Here we see two spheres that are about to collide. Now the masses of the spheres don't have to be the same. The masses could be completely different actually. There are no external forces acting on the system. So that means that if the spheres don't collide, they would continue with the velocities that they have forever. When the spheres collide, of course, there are internal forces on the system. There's a force on sphere 1 due to sphere 2, that's written F12, and a force on sphere 2 due to 1, that's written F21. Sometimes, by the way, you'll see this written the other way around. You might see this written as F12. That means the force due to 1 on sphere 2, but I prefer the other way, so let's stick with it. Now we can apply Newton's third law. Newton's third law says that when we have a force on one object due to another object, we have an equal but opposite force on the second object due to the first object. Now, Newton's third law might seem obvious for the case of two identical spheres. But the spheres don't have to be identical, as I said earlier. One sphere could be much more massive and indeed much larger than the other sphere. We could imagine a sphere like this. It's much more massive. It might have 10 times more mass than this second sphere. But Newton's law still holds. These two forces will have the same magnitude, even though that might seem counterintuitive. Now let's apply Newton's second law to the situation where the spheres are colliding. So Newton's second law says that the average force on sphere 1 due to sphere 2 is the mass of sphere 1, which I'll write as m1, times the average acceleration of sphere 1, which I will write as a1. So you see, it's possible that these forces are not constant forces. You know, when the spheres first collide, the forces between them might have a certain value, and that might change as the spheres become slightly deformed. I'm not sure whether the forces between them, these two forces, remain constant all the time. You know, it's possible that this one increases during the deformation of the sphere, but of course this one will always increase in tandem with it. So for each instant that the spheres are colliding, this relation holds, Newton's third law holds, and of course Newton's second law holds. So F12 could be changing with time. So that means that the acceleration of sphere 1 is changing with time. But the main point is that even if these forces are not constant during the time that the spheres are colliding, Newton's third law still holds for each instant, and Newton's second law holds. So let's look at the force on sphere 2 due to sphere 1. Well, that's the mass of sphere 2 multiplied by the average acceleration of sphere 2. So these are the resultant forces because there are no other forces. There's no external forces on the system. Now you might say, what if these spheres are on a surface that's near the Earth? You might say, there's an external force. You have the weight of the spheres to consider. Well, that's true, but that weight force is counterbalanced by the contact force, or the normal reaction of the table or whatever, to the spheres. So the sum of these two forces will be 0. So the resultant force on the spheres is entirely due to the contact forces between the spheres. It's all internal forces. So we don't have to worry about, you know, gravity or the reaction. They add up to 0. We don't have to worry about friction either, because we will assume in all the problems that we see that, you know, the spheres are slipping along a perfectly smooth surface. So there's no friction force opposing the motion. We don't have friction forces opposing the motion. In that case, actually, the sphere won't even turn. So we'll see that in the section on angular momentum later on, that if there's no friction force whatsoever, a circular object will not roll. So these objects are not even rolling in the ideal situation of no friction. They're just slipping along the surface. So this point is always in contact with the surface. So that's the ideal situation. Slipping spheres. We don't see this in real life, of course. We always see something rolling, so it might be a little bit counterintuitive. But that's the theory that we're working with. We're assuming no friction, no external forces. or if there are external forces, the external forces all cancel out to zero. So these become the resultant forces. Okay, so I've applied Newton's third law and Newton's second law, and now we're going to write these average accelerations in terms of the change in velocity of the spheres. So in the event that the forces are not constant, well, the accelerations won't be constant either, so we are talking about average accelerations here. So we're talking about the average acceleration over the time that the spheres were colliding. So, you know, you can imagine that this time is extremely small. That's the time that the spheres are in contact with each other. So what is the acceleration? Well, it's the change in the velocity. So it's the velocity immediately after impact. For sphere 1 we'll say that that's v1. That's a vector. Minus the velocity immediately before impact. And we're calling that velocity u1. And similarly for the acceleration of the second sphere, it's the change in its velocity divided by the time taken for that change to occur. So t is the time of collision. So the key point here, of course, is that the time of collision is the same for both spheres. So we can multiply across by that time. Okay, so multiply m1 into the left and m2 into the right, and then rearrange. So I've brought all the terms involving u to the left hand side and the terms involving v to the right hand side. Now notice that we have products of the form mass times velocity. Now these products are called momenta. So if an object of mass m has a velocity v, the product of its mass and velocity is called its momentum. You can see that it's a vector quantity, because the velocity is a vector quantity and we're just multiplying the velocity by a scalar. So what are the units? Well, it's clear that the units are mass in kilograms, velocity in meters per second. Another way that we can write this actually is the Newton second. You can see that if you go back up here, the units of force is newtons. So this thing here is in newtons, but we multiply both sides by t to get rid of the t. So we're multiplying, so the units are newtons times the units of time, which is seconds. But notice this quantity on the left hand side. It's just the sum of the momenta of the particles immediately before collision. And it's a vector. It's a vector sum. We refer to this as the total momentum of the system before. The system consists of just the two masses. And here we have the total momenta of the system after the collision. So this means that the momentum is conserved. Conserved means that it doesn't change. The same before the collision as it is after the collision. And it never changes, of course, as the spheres continue to recede from each other. Because if there are no external forces, these velocities v1 and v2 never change. If the velocities never change, the total momentum after the collision never changes. Now, let's apply what we know from the previous video and this video to solve this particular problem. In the previous video, we explained that the final velocity of A relative to B is minus e times the initial velocity of A relative to B. We could also use this equation. The velocity of B relative to E is minus e times the initial velocity of B relative to A. That's because the velocity of A relative to B is just minus the velocity of B relative to A. So you could use either of these. You know, it's just a sign change, essentially. If we change all the signs of this equation here, we get this second equation. So we assign a positive sign to an arbitrary direction. So I could make vectors pointing to the left positive or vectors pointing to the right positive. Normally we just take vectors pointing to the right to be positive. So VAB is just VA minus VB. So we can write our equation like this, and we can get the relative velocity of A with respect to B after the collision. We don't know what VA and VB are. So what's the initial velocity of A? Well, it's 3 meters per second to the right, so its velocity is plus 3, minus the initial velocity of B. Well, it's 2 meters per second to the left, so it's minus 2. E is a half. So, based on what we covered in the previous video, we know the relative velocity after the collision. But we don't know the actual velocities of the two spheres after the collision. We obviously need a second equation in VA and VB, and we get that by applying the conservation of momentum to the two spheres. So on the left hand side we have the total momentum of the system before the collision. On the right hand side we have the momentum after the collision. Now we can apply conservation of momentum because there are no external forces. That's important. I explained to you before that force of gravity is cancelled by the contact force on the sphere due to the table. Also, we are given that the spheres are smooth and the table is smooth. So, as the sphere moves to the right, no force is exerted on it. So there's no friction force. So that actually means that this sphere doesn't roll, it doesn't turn. So it just slips along towards B, and the same is true for B. B just slips along, so this point of the sphere is always in contact with the table, and so is this point of sphere B. The mass of A is 4 and the mass of B is 1. The velocity of A is 3 and the velocity of B is minus 2. So we get our second equation in A and B. So we have a pair of linear simultaneous equations. I'll write this top equation in here. And I'll add these equations together. These equations are easy to solve. So we have 20 over 2 minus 5 over 2. That's 15 over 2. So VA is 15 over 10, which is 3 over 2. So plug this into one of these two equations and you get VB equals 4 meters per second. So here is the situation immediately after the collision. The velocities of both spheres come out to be positive, which means that both spheres are moving to the right. Now, in another video I will discuss kinetic energy in more detail. Here I'll just go and do the calculation. It's straightforward. Kinetic energy is a scalar. It's half the mass times the speed squared. So to get the initial kinetic energy, all we need are the initial speeds. So working that out, we get 20 joules. For the final energy, again we just need the final speeds. We don't have to worry about the signs. Anyway, we're squaring, so for this answer we get 12.5 joules. So you can see that the kinetic energy is not conserved. And that's always the case for inelastic collisions. Okay, we always have some loss in the kinetic energy when E is less than 1. So, and of course in reality all collisions are inelastic. Now if you have a perfectly elastic collision, that is when E is equal to 1, you will find that the loss in the kinetic energy is 0. So that means if the initial kinetic energy was 20 joules, the final kinetic energy will also be 20 joules, no change. So for inelastic collisions, E less than 1, essentially all collisions, there are no ideal situations where E is equal to 1, there is some loss of kinetic energy. The kinetic energy after the collision will be less than the kinetic energy before the collision. That loss of energy, in this case 7.5 joules, is the energy that goes into deforming the two spheres. When the two spheres collide, we get deformation of the two spheres. Let's take this example here, where we have a sphere of mass m moving directly towards another sphere, an identical sphere of mass m. The second sphere is at rest, its speed is 0, but the first sphere is moving with some speed u. Now u can be any value, u is some non-zero value. Let's assume also that we have a perfectly elastic collision, that is, the coefficient of restitution is 1. I just refer to this as an elastic collision, as opposed to an inelastic collision where E is less than 1. So we know that regardless of the masses of the spheres, this relation holds. The relationship between the relative velocity of the spheres after the collision and the relative velocity of the spheres before the collision. So we just fill in the initial velocity of sphere A is u. It's pointing to the right. I'm taking directions to the right as positive. So u is the speed, u is a positive value because it's a magnitude, so we could put in a plus to emphasize the vector instead of the speed. Okay, ub, the initial speed of b is 0. So va minus vb is just minus u. Next we get a second equation using momentum conservation. So again, I'm assuming that there are no external forces acting on the system. So let's look at the momentum before the collision. Well, it's the mass of sphere A, which is m, times the velocity of sphere A, which is u. So u, remember, is some positive number. Okay, it's pointing to the right in the positive direction. Now what about the momentum of sphere B? Well, its velocity is 0. Now let's look at the momentum after the collision. So the momentum of sphere A is mass times its velocity, plus the momentum of sphere B, which is m times the velocity of sphere B after the collision. Notice here that we can divide out by the mass. So VA plus VB equals u. So it doesn't matter what mass we start with. So I just call the mass of the two spheres m. They could have been 5 kilograms each or 10 kilograms each. It makes no difference to the solution of this problem because m cancels out. So we solve between these equations. This is easy, just add them together. So we get twice VA equals u minus u, which is 0. So after the spheres collide, VA, the first sphere A, comes to rest, it stops. Okay, what about VB? Well, if we plug 0 in for VA in this equation, we get VB equals u. So here is the picture. So up here we have the situation just before the collision of the spheres, and down here we have the situation just after the collision of the spheres. So it looks like all the momentum of sphere A gets transferred to sphere B. The momentum of sphere A is mass times its velocity, and after the collision the momentum of sphere A drops to 0, whereas the momentum of sphere B is now mu. It was initially 0. Here is a simulation. Both spheres have the same mass. I've set the mass of each sphere to be 1, but I could set it to be any number. The coefficient of restitution, or the elasticity E, is set to 100%, which is 1. The speed of the first sphere is 1 meter per second, so that's our U. I can set that to anything I like. You'll see that speed getting transferred to the second sphere. I should mention the initial and final kinetic energies of the system. The initial kinetic energy is the kinetic energy of the first sphere, which is half its mass times the speed squared, and the kinetic energy of the second sphere, which is 0 because the second sphere is at rest. After the collision, the first sphere comes to rest, so its kinetic energy is 0. The second sphere moves off with the same speed as the first sphere, so its kinetic energy is a half mu squared. So these are equal, so there's no loss in kinetic energy. And as I explained earlier, that's the case when we have an elastic collision, when E is equal to 1. So no energy goes into the deformation of the spheres when the spheres collide.